Okay, so our goal by the end of this video is to be able to correctly calculate z-scores and also be able to interpret them in a variety of settings. So a z-score or a standardized score results from this process called standardizing, which is when you change the original data values into standard deviation units. So formally, we define the standardized score or z-score as if we're going to assume that x is going to be our data value, and it's in a distribution that we have that we know the mean, so mean x bar, let's say, and we also know standard deviation, so we know the mean, standard deviation. Then the standardized score for z is going to be equal to that x value minus the mean divided by the standard deviation. Now, what is a z-score? Like, what's the point of this? Well, a z-score basically is a great way to compare common groups of individuals. So to kind of get a sense of how you compare or how an individual compares with groups that are like them. So it's similar to like a percentile. Like, let's say let's say you want to figure out, are you a tall person? You're gonna basically look at what percent of people you're taller than, right? If you're going to be taller than, if your height is taller than about 90% of the population, then you're probably going to be tall. Now, the thing is what about if you want to figure out if a 5-year-old, kid is tall, or if, a newborn baby is going to be tall? Because, you're not going to compare, the height of a newborn baby, to the heights of full-grown adults, because their heights are obviously not going to be comparable. You're obviously going to be like, oh, this baby's short. But that's when we look at it in the absolute sense, in terms of just the absolute value. So like if we look at the height of the baby, maybe it's 2 feet, and we compare it to someone 6 feet, we're going to say that they're not tall. So what we're going to need to do is compare the heights of that newborn baby with the distribution of heights of newborn babies, because then that's going to give us a sense of if that baby's going to actually be taller than the average person. That's a way we can predict if they're going to grow up to be taller than the average person or not. Like another example is standardized scores used a lot in the medical field. Let's say you go to the doctor and you want to see if you have weak bone density, and let's say you're like a 40-year-old woman. Now the doctor's not going to compare your bone density to just the entire population. They're going to look at the distribution of females that are about 40 years old, and they're going to see like where your bone density lies comparatively speaking. So they're going to have to standardize your bone density into what's called a z-score. So it's used a lot in the real world. So a z-score tells you how many standard deviations a value is from the mean. So if it's positive, that means it's going to be above the mean. If it's negative, that means it's going to be below the mean. So you're going to be below average. If it's equal to 0, then that means you're going to be exactly average, because you don't vary at all from the mean. Now, to really gain a good understanding of how z-scores work, let's go through a practice problem, because that's always the best way. So here we have a scenario where we have the mean number of wins in Major League Baseball was 81 in 2012, and their standard deviation was 11.9. So we're going to find and interpret the z-scores for the following teams. So the New York Yankees had 95 wins. So if we calculate their z-score, this will be our x value. That'll be 95 minus the mean. The mean was 81. So let's go ahead, let's just write x bar is 81. So 95 minus 81 divided by the standard deviation, 11.9. So let's go ahead, let's calculate that. 95 minus 81 divided by, and we get roughly about 1.18. So then we say that the New York Yankees had about 1.18 standard deviations above the mean number of wins. At about 1.18 standard deviations above the mean number of wins. Now the New York Mets had 74 wins, so their z-score is going to be 74 minus the mean, which is still 81, over 11.9. We're going to get a negative value. 74 minus 81 divided by 11.9, about negative 0.59. So we say that the New York Mets had about 0.59 standard deviation wins below the mean amount. Below the mean amount of wins. Now, always keep in mind, the context of the problem, because you don't want to rely on formulas and then you lose your thinking and make some, ridiculous mistake. Because, if the average number of wins is 81 and the New York Yankees had 95, we know that they're better than average, because 95 is more than 81. The 1.18 just tells you a numerical, quantity that gives you a more precise way to, say how much better they were. And same thing, or similar to the New York Mets, they had 74 wins, so they're below the average number of wins. This 0.59 just tells you a numerical, quantity that gives you a better idea of exactly how far below the mean amount of wins they were. So let's look at one more problem. And again, this is real data. And in here, we're going to compare, 4 baseball players. And if you haven't caught on, in baseball, the stats is used a lot. So you're going to see a lot of problems dealing with baseballs, because it's a sport that really relies on statistics. So here it says that the single season home run records for Major League Baseball was set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 1961, Mark McGwire hit 70 in 1998, and Barry Bonds hit 73 in 2001. So in the absolute sense, Barry Bonds had the best performance of the 4 players, because he had the highest number. But in a relative sense, this may not be true, because in different time periods, we can argue that hitting a home run was easier and harder than in other time periods. And this is due to factors like the quality of the batters, the quality of the pitchers, the material of the baseball, the dimensions of the ballpark, what size they are. And we know that some of these guys were using drugs, and they probably didn't test as heavily in some periods of time than others. So to be fair and gauge how good they were to the other players in their time period, we're going to calculate z-scores for these 4 individuals during their eras. So here are the values. So the home runs, that represents our x values. The means, our x bar, and standard deviation, our sigma. So for Babe Ruth, that's over here, let's calculate the z-scores. So for Babe Ruth, his z-score would be equal to 60 minus 7.2. Wow, that's way above. Geez, 60 minus 7.2 over 9.7. I already tell us any big numbers, or relatively big numbers. 60 minus 7.2 divided by 9.7. We'll get about 5.44. For Roger Maris, our z-score will be 61 minus 18.8 over 13.4. That gives about 3.15. Mark McGuire will have 70 minus 20.7. 70 minus 20.7 divided by 12.7. We'll get about 3.88. And for Barry Bonds, his z-score would be 73 minus 21.4 over 13.2. I think it was about 3.91. So as you can see, Babe Ruth has the highest z-score. It's by by a good amount, by almost 1.5. And what this is saying is that compared to the players in his time, he was far greater. He was much more dominant than the other players were during their times, because he was 5.44 standard deviations above the average amount of home runs. So we could say that Babe Ruth appears to be the most dominant player during his era. Appears to be the most dominant player during his era. During his era, which is why he's known as a great.